Hello, this is Scott Dahman of Power World Corporation. In this section, we'll take a look at some of the advanced features of Power World Simulator's contingency analysis. We'll talk about some of the other features of contingency analysis that we did not get to in the first course, and these allow you to do things like change the behavior of limit monitoring just for the contingencies. You can do different things with like distribution modeling through load flow throwover records. You can change generators' response and make it different than it would be in the power flow for certain things. And then we'll also take a look at some of these other displays that we didn't look at in the intro course for looking at results just in different ways. Finally, we'll take a look at conditional actions, which can be used for remedial action scheme modeling. So things that might happen during a contingency, perhaps as a response to an outage, and actions that would only be taken if certain conditions are met. Like, for example, if the interface is heavily loaded, then maybe if a contingency occurs, then it makes a redispatch of some generation, or it drops some generation to relieve that interface so that it doesn't become a violation in the post-contingent state. Okay, so we will use the Eastern.pwb case, which is a larger model of much of the Eastern interconnect is a example for this, because we can punch in a whole bunch of contingencies and experiment with the modeling stuff. So we'll go to File, Open Case, and then choose the one called Eastern.pwb. We'll do some review of the basic stuff, of course. In order to set up our contingencies, we'll use an auto insertion. So again, to get to the contingency analysis, we go to our Tools ribbon, and then we choose Contingency Analysis. And we'll do an auto insertion. So we'll come down here, we'll click Auto Insert. And we'll leave all of these defaults here. We will want to apply area zone filters just so we don't put contingencies in across the whole system. And we're going to apply, we'll click the Edit Area Zone filter. We will apply a filter that will ignore everything except Area 25. So we could toggle, right now we've got 25 through 35 that are set to yes. We can toggle everything to no. You can click and fill, or you can use the set drop down. Set everything to no except for area 25. We'll set that to yes. And then we'll close that. The rest of the defaults can be left, and we'll do an insertion. And the confirmation dialog tells us we're about to insert 111 contingencies, and we can say yes to that. Okay, another thing that we want to do, just in order to make an initial run of the contingencies go faster, is we will use the linearized lossless DC calculation method. So going to my Options tab, we'll choose the center. Second option for the calculation method, linearized lossless DC. We might also want to choose for makeup power to use the generator participation factors from the entire case instead of sending everything to the slack bus, which is what the first option would do. if we don't populate any makeup power factors by area. So then we'll go back to the Contingencies tab, and then we'll click Start Run. And using the DC method, it should process the 111 contingencies fairly quickly. And one thing we might notice is that there are a whole bunch of violations for every contingency. And the maximum branch percentage is the same. And there's not much difference. We click on one contingency and then we click on the next one. And there's not a whole lot of difference in terms of what shows up down here as violations. And the reason for that is most of these are base case violations. We did not change anything in our limit monitoring settings yet in this case to only look at certain areas or only look at certain voltage levels or to ignore certain things. So anything that's a violation in the base case is going to generally be re-reported right now, and there's an option in the contingency analysis to ignore those or to modify at least how they get reported. So we'll go to the options ribbon, and then there's a group down here called limit monitoring. We'll open that and we'll choose the advanced limit monitoring page here. And on the right side of this dialog, we see there's an option group for re-reporting of base case violations. The default is just to list everything for all contingencies. So if you have a base case violation, that's still a violation during the contingencies run, it's just going to be re-reported. So how you might address that is you might might go to your limit monitoring settings, as we did when we discussed that topic, and just not report certain things. Or if we still generally want to report everything, but for the contingency analysis we only want to look at things that have changed or gotten worse, we could alternately say to just not report base case violations. So anything in the base case that's not exceeding the contingency rating would not be reported in the contingency analysis. So if we choose that, we can come back in here. We could rerun the analysis, but another thing that you can do in the contingency analysis is if you change the limit monitoring set such that the set becomes more restrictive than what it was before, then you can simply tell it to filter out those violations that it already calculated and reported that are no longer violations based on the current rules for limit monitoring. So to do that, we can go under the Other tab and choose Filter Results using limit monitoring settings. And if we do that, then just a lot of them disappear then. That trick doesn't work if you expand the limit monitoring set, because when it did the run originally, anything that wasn't a violation wouldn't have been recorded. If you expand the set of violations, you would have to rerun the analysis in order to catch those, because again, it still has everything in memory that it had before from the last run, and it's just filtering out that list, so you see fewer items there. As far as base case violations goes, there's also a third option, which if you choose that, you can specify thresholds for which to ignore the base case violations. And generally you would want to put small values in to say that we want to ignore the violations if the change is less than a certain percentage. So if you have a base case violation and then you run a contingency and the contingency doesn't affect the base case violation very much, then maybe you don't want to report it. But if the contingency makes it a lot worse, then maybe you do want to report that, as opposed to just simply ignoring it because it was an overload in the base case, as we did with the first option. So for example, we could choose to say, let's ignore violations if the increase in line and transformer flows is less than 5%. And then you could put a similar threshold in for changes in per unit bus voltage, which really isn't applicable here because we're using the DC calculation method. So it's not really computing changes in bus voltage. But if you're doing the AC calculation method and you had some bus voltage violations, you could put in some thresholds for changes in bus voltage on the low side and on the high side. And then you can also put a percentage for interfaces if you have those. This particular case doesn't have any interfaces as saved, so that's irrelevant. But if we go back to the contingencies, even though we changed the monitoring set to expand it a little bit, it's still more restrictive than it was in our initial run that was in the memory. So we could come down here and do another filtering of results using the current limit monitoring settings, and it could bring some back in. It's like on this first line, I think it brought one in. On this contingency, it added one. So there's some more violations that are included. Of course, we can sort by violations and see there. So that's kind of a hybrid option there. Then on the left side, there's similar options, but it doesn't have to do strictly with base case violations, but with any change relative to the base case or relative to the reference state. So the first grouping is for never reporting violations if the changes are below a certain threshold. So this pertains to anything, not just base case violations. You could have a situation where an element is not overloaded in the base case, but then becomes overloaded. But in becoming overloaded, if the change is below a certain threshold, you can still tell it to ignore. So, for example, if you had a loading that went from 99% of the limit to 101% of the limit, normally that'd be considered a violation, but you might say, well, the change is really small, so I don't want that in my results. So you could put a threshold in there, like, for example, 5% or 10% or whatever you want. I mean, generally, it's assumed that you put in some small values here, which is why they default to 0. And again, you can do the same thing with line and transformer flows, and interfaces can be percentages, and then the bus voltage violations can be per unit. And again, on this, we could check and see if there's anything that gets ignored. So I might see, before I filter my results, I might see, for example, how many violations I have right now. It says that there's 98 down here, but I believe that's for the first run that we did with everything. I could look at the column metrics here and see, oh, okay, there are 98 that are in this set right here. If I apply the filter with the new restrictions, then some of them disappeared. So it looks like it still says 98 down here, but I could do a column metric look here, and I see now I have 52. So the difference between 98 and 52, what would that be, about 46 or something like that, got eliminated because the change in branch flow was less than 10%, so it ignored those. Then you can also do the opposite, where you can always report as a violation large changes. And this is regardless of whether or not it actually exceeds the limit or not. So for example, maybe if a contingency causes a change in flow of at least, let's say, 40%, then I want to see that reported in my contingency list, even if the change doesn't result in a limit violation. And again, you can do similar things with voltages and interface flows. Now with this change, I'm making the monitor set, I'm expanding it to possibly include additional things that weren't reported before. So now I would have to rerun my contingency analysis in order to pick that up. So I could see if I had any of these, it would show up as a category of change. So here, if I go to the second one, if I'm sorted in descending order on number of violations, and I go to the second contingency right here that has 16, I can see that some of them have a category of change branch MVA. So here's one right here. This is a line in the system. It has a limit of 426 MVA. And in the post-contingent state, it's still only loaded at 71% of its rating. But because of the change from the reference state being greater than that threshold I put in there, it gets reported as a violation. So you can see those as well, if you want. And then if you're doing the AC analysis, you can also optionally report changes in bus DV/DQ sensitivity. This is something that we explore in an example in our security analysis course, but not so much here on the market side. But if you're doing a full AC calculation method, then you can use this option, and what it'll do is it will compute the self-sensitivity, basically the same thing you get under here on the sensitivity analysis when you go to flow and voltage sensitivities. It'll look at the DV/DQ sensitivity of reactive power injection at each bus and how that changes the voltage at the bus. And then it'll compute that in the reference state, and it'll also compute it for every contingency. And if the change under the contingency exceeds a certain multiple, then it'll report that as a violation. There's a note the simulator gives over here in the right that just says, be careful because this can increase the processing time to calculate all the self-sensitivities, once for the reference state and then once for every contingency. It suggests that you use a bus filter. So you might want to have a filter that looks only at low voltage load buses or certain buses in a certain part of the system that are susceptible to changes in DV/DQ sensitivity. So we won't do that here. And then you can optionally have it report as a violation any contingency that causes a bus to become disconnected from the rest of the network. So, and then those would be reported as their own category. All right, I'm going to set this all back I'm going to clear the box for always reporting as violations here, and also the one here on never reporting. Go ahead and leave that one the same. And then I can come back here and just filter, again, the results using the current limit monitoring settings. And that'll remove some of the contingencies. The next thing we'll take a look at is what's called monitoring exceptions. And what this can be used for is kind of in place of, it's kind of a short, simplified substitute to doing a remedial action scheme. You might have a situation where you're running your contingency analysis and you know just from personal experience that some of the results that come up in the violations aren't really problems in the real world. And if they're not really problems, it's probably due to some remedial action scheme that is, protecting some part of the system during a certain contingency so that there aren't any overloads during that contingency. So, one way you could do that is you could just completely ignore those elements from monitoring, but that would ignore it for all contingencies, and it would ignore it in the power flow as well, which you may or may not want to do. You could also model the remedial action scheme, but of course that requires the data in understanding what the remedial action scheme is, and you may or may not have access to that. But certainly if you're doing something like running a security constrained optimal power flow, which we'll take a look at in the later section, where you're asking the program to relieve the base case and all the contingent violations, you don't want it to dispatch generation around contingent outages that aren't really problems because of remedial action schemes. So one way you could accomplish that is you could just tell it to ignore certain overloads for certain contingencies. So for example, if I look at this contingency right here that represents the outage of the Conditional to Hunterstown 500 kV transmission line here, I can see that it has several outages. One of them, for example, looks like the worst one is this transformer here, but there's a transmission line between Roxbury and Green, 138 kV transmission line, and again, maybe we just want to ignore that outage because we know there's some sort of operator action or remedial action that alleviates it. So we could go to our options, and then we could go under limit monitoring. We can choose monitoring exceptions right here. And then these exceptions are listed as pairs of contingencies and monitored elements. Those are the key fields for the monitor exception records. And to insert one, of course, we can right click in the grid and then choose insert. So with you pick the contingency up here and a monitored element down here. So for the contingency, we'll click the change button and we'll choose the contingency Conditional to Hunterstown, I think. So this one right here, between 4 and 26. And then click OK. And then we can choose to exclude the transmission line from Roxbury to Green. And looks like if we're sorted by name, we can just come down here and start typing Roxbury and find the 138 kV bus, which is this one right here, number 233. And then at the far end, choose Green. And then you can choose, for the status, you can choose include, exclude, or default. Exclude means ignore that element for that contingency. Include means always monitor that element during that contingency, which you could use if you were otherwise ignoring that element. And then default means just temporarily disable the monitoring exception and use whatever the limit monitoring settings would dictate. So now I've got the record is added, and you can add as many of these as you want. If I go back to my list of contingencies now, and then here I see that particular overload being reported. If I chose to filter my results using the limit monitoring settings, then that one disappears. So now I just have the other 3 for that outage. So another option underneath limit monitoring here is called custom monitors. And what you could do with that if you wanted to is you could monitor, let's say, the flow on a particular interface or a line during every contingency all the time. So like always report that. You're just always monitoring that regardless of whether or not it's a violation. And to do that, you just right click in there and choose insert. And then you can give it a name, and then basically you just choose what you want to monitor. So down here, you can pick all objects of a specific of a type. So for example, if you wanted to monitor the flow on all of the interfaces, you could do that, or you could choose specific objects. So that's this option right here. And then, you could pick, for example, transformers, and then you could pick a specific transformer, and then you can choose to, different filters in different fields. So like, for example, if I wanted to look at the MVA flow in the transformer, and then you can tell it to only report violations if there's an increase in the field value or a decrease in the field value greater than a certain threshold. Or like particularly if you're choosing all objects of a certain element type, you can put a pre-filter or a post-filter, which will either filter on reference state conditions or post-contingent conditions, and so forth. So we're not really going to do an example with this, but if there's something you always wanted to track during contingency analysis, you could do that through the custom monitor. Okay, so the slides just go through some of the things that we've just talked about as far as advanced limit monitoring. It's also worth noting too on this, some of these advanced limit monitoring features are also available for limit groups in limit monitoring. So if I go to my limit monitoring settings and I open the dialog for a limit group, I'll go to the Modified Create Limit Groups page, right click on here and choose Show Dialog. There is a tab here called Contingency Options, and you could, if you check the box that says Use Group Specific Contingency Options, and it enables all this other stuff. And then you have these things for never report small changes or always report large changes. Same idea as what we looked at in the advanced limit monitoring in the contingency dialog, but this just applies to everything in the limit group that it's associated with. And if you do have settings like this that are applied, if you check this box and apply these settings to certain limit groups, then for that limit group it would override the settings that you see under contingency analysis and advanced limit monitoring. So just the relevant categories. Okay, so this slide describes what we did with the monitoring exception, and also for custom monitors. It's also worth mentioning that the custom monitors can only be calculated and measured if you're using the full power flow calculation method on the contingency options. So if you're using linear methods to compute the contingent flows, then it won't report those for the custom monitors. Okay, the next feature here is contingency blocks. This is something that you can do if you have a list of actions that occur in more than one contingency. It's a good shorthand for you. You can just define the block once and then reference it in other contingencies. To access those, you go under the options here, and then under, let's see, it's actually under legacy definitions, because we're kind of, with the new remedial action scheme feature that we'll talk about shortly, it kind of reduces the need for contingency blocks, but you still might use them if it's just a collection of actions that are used only for certain contingencies. So there's just a note up here that it's kind of an obsolete function that's being replaced with remedial actions, but if you want to use them, you can right click, and defining one is just like defining a contingency. So you just right click and choose insert, and then this dialog looks just like the dialog for creating a contingency. You can give the block a name, and then you can insert one or more elements into the block. So just like you're defining actions in a contingency, and you have the same different element types over here. So, and then if you create one, you can reference it inside a contingency definition by just adding the block as an element inside a contingency. So for example, on this contingency, I've got one action associated with it because I auto-inserted a bunch of single action outages. But if I wanted to put another action onto that contingency, one of the options that I have is to reference a contingency block. So if you've created one or more blocks, you can choose those, and then it'll just apply all of the actions in that block with that contingency. So there's some other features that are described in the slides, which again are kind of going away because of the new feature for remedial action definitions. Global actions, again, this functionality is being replaced by remedial actions, but it's still there. If you have some that were created in the past, you can continue to use those right now. So next we'll take a look at a feature called bus throwover records, and what this will do is it can be used to model distribution actions in a power flow model, which typically doesn't have much, if any, detail of the distribution network. So for example, if we look in our case at the bus view one line at the this 138th Street bus, which has loads at lower voltage buses, 9225 and 9226. I can call those up on the bus view one line just by opening that, and then I'll just type in 9225 for the bus. And that takes me to this load. So there's a step-down transformer and a load, and this probably represents a distribution feeder that goes out to a distribution network and includes several loads. And there's another one in parallel attached to a different transformer, and it could be that the distribution network is set up where there's some, between these two feeders, there's some normally open breakers. And perhaps if this transformer goes out of service, some or all of the load that's modeled right here could possibly be thrown over to this bus. So if you wanted to model that in the contingency analysis, you could create a load throwover record. So I'll go over to the options, and then under modeling, go to bus load throwover. And then all you do with this is it's just a list of bus records that has just the basic bus number and name and nominal kV fields, and then the throwover records. So you could go to, in the list, I can jump down to number 9225. I need to choose number up here. And then just enter 9226 as the throwover record, and then vice versa. So, and then once you type in the number, it just populates the name and nominal kV, and then just another format for it right here. So then again, what that does, anytime you have those the alternate bus stored for each bus, anytime the load at that bus gets disconnected, it would move it over to the other bus. And you don't have to, it's just done internally. You don't have to mess with changing the load at the bus as part of a contingency definition. Okay, and you can also change how generators are modeled in the post-contingent state. And normally, if a generator is AGC-able, so if its AGC field is set to yes, then it could be used for makeup power, according to the high-level rule that's set on the modeling basics tab of the options for where the makeup power comes from. And then next, you can set characteristics of individual generators. So the first one is one called Generator Post-Contingency AGC. And if you go to that tab, this is just a case information display with generators. And it shows the participation factor field, and then whether or not it should prevent AGC response in the post-contingent state. The default is no. And no basically just means to look at the AGC field for the generator, which is shown here. And if it's AGC-able, then it could be used for makeup power, assuming it's not at a limit. And you can also choose as a value for the prevent AGC response, yes. If you choose that, it will, regardless of whether or not the AGC is set to yes or no over here, it would block that generator from moving in the post-contingent state. So you're preventing the response. And then the third option is to force a response. And if you choose that's respond, it's the value that corresponds to that. And then even if the generator's AGC field was set to no, it would respond in the post-contingent state. So, and then you can also have a participation factor that's different in the post-contingent state than it is in the power flow if you want. So by default, the value of the post-contingent participation factor is equal to same, which just means it'll use the same participation factors over here. You can also put a limit on how many megawatts of response each generator is able to give. That can be more restrictive than just the minimum and maximum capability of the unit. So, for example, if you put a number in, let's say 10 megawatts for this particular unit right here, what that would mean is that in no circumstance could that unit be called on to dispatch more than 10 megawatts or change its output by more than 10 megawatts in the post-contingent state. So you can put in values there. If you want to clear the value, you can just type in like a space and then hit enter, and that'll clear it. And if there's no value in there, that means it's only capped by the minimum and maximum megawatt capability of the unit. The next feature listed here is line drop and reactive current compensation for generators. And normally, there's a good slide which illustrates this behavior. As we kind of scroll through, there's some slides on the maximum megawatt response and also the post-contingent AGC. The next one shows line drop and reactive current compensation. And normally generators are regulating a specific bus in the system, the voltage at a specific bus. That could be the terminal bus or it could be a remote bus, but it's varying its reactive power in order to meet the set point of a bus. You can alternately tell the generator to regulate a fictitious, the voltage at a fictitious bus that's a certain impedance down away from its terminal. So this represents a terminal bus. This represents like the next transmission line in the system. And then this bus is a fictitious bus that is this impedance away from the terminal. And you specify with the dialog the value of the real and reactive per unit impedance of in this block right here. So looking down the line. And those values can be positive or negative. So if they're positive, it's generally like looking down a transmission line. If it's negative, it's looking back into the machine. So, and then you have to tell it whether or not to use this feature. By default, it doesn't use the feature. The generator is just regulating a bus. If you choose yes, it'll use that feature in both contingency analysis and in the power flow. If you choose post-contingency, it'll only use the feature in the contingency analysis. Okay, and then finally, you can also make other changes if you wish to the behavior of the post-contingent power flow that are not specified in these other features. So if you want to do that, you can create an auxiliary file with those settings and then just point to that auxiliary file right here. And then it'll load that file actually at the start of each contingency, so after it applies the reference state, but before it runs the contingency. And then so when it does the solution after the contingency, those settings would be used. And then after it processes each contingency, it goes back and restores the reference again, and then applies the auxiliary file. So some examples might be you could change the AVR settings, the automatic voltage regulation settings of a generator to different, have different availability, or change the reactive capability curves, just some examples. But it suggests in here that you only change values that are actually stored in the reference state, because if not, then it would load that auxiliary file and then permanently change your case. So these are, again, another list of variables that are stored in the reference state. So if you change any of these, they'll get changed back properly when the reference state is restored. If you change anything else, then it could make a permanent change to your case. All right, under the other button, there's also some features for just looking at data in different ways. We've looked at, up to this point, browsing results by looking at the list of contingencies. And then there's some summary statistics on how many violations and what the worst violations are of different types. You could click on a contingency and then look at a list of corresponding violations down here. You can also go to the Results tab and look at, for example, overloaded lines. Click on some of those and then see corresponding contingencies that cause outages on that line, or overloads on that line. And then you can also look at what's called like combined tables, which put those different tables that you can look at in different panes into a single view. And they're available under this combined tables view, and then also under other. You can go other combined tables, and then the same list of options is available. So one of them is a contingency violation list. We'll start with that one, which is actually the second option in there. And what that does is it puts every combination of contingency and overloaded element into a table right here. So, and of course you can sort and filter that if you want. There's also a list of contingency element definitions. So you get just a flat file with those. So if a contingency has 10 actions happening in it, then you would see the contingency label repeated 10 times with different actions in here. So going back to the violations, there's also a contingency violation matrix, and you have to tell it then what to process. So it'll build a matrix when you click the process button, and if we include everything here, it lists any contingency that has at least one overload as a row, and then any element that's overloaded at least once will be a column, and then it'll show the value of the corresponding violation. So just another way to look at the results. And then finally there's a what actually occurred table, and this is it's more interesting when you have remedial action schemes, because then you have actions that might occur under certain conditions and might be skipped under others. Here it just shows in our case we have 111 contingencies, each with one element, so they're just all shown, and every action is shown as having been applied. If it was a conditional action that was skipped because the condition wasn't met, then it would be skipped. So, okay, there's also, under the other tab, you can tell it to dump out a text report, and to do that you just specify the name of the text file, and then you look at it, and then typically inside the text file it'll have a list of the contingencies and the violations. You can specify to some degree what goes into that text file. If you go under Results tab up at the top, and then Text File Report Writing, there's just some check boxes and other options. You can tell it what to include in the report. And then there's also a Produce Report button there, so again, which will then dump that information out to a text file. There's also the ability to do a comparison of contingency results, and we don't really do a detailed example in this section, but there's another training section in the security analysis course where we do an example. And this can be useful for if you're making like a major change to your case and you want to run the set of contingencies on the before and after. For example, maybe there's a generator interconnection that you're wanting to study. So you can have a base case without the generator interconnected, run a bunch of contingencies, save the results out to a file, then change the case in some way, for example, interconnecting a new generator, run the same set of contingencies, and then compare the results from the two cases, one without the generator and one with. And you would access that under the other tab down here, and then choose Compare to Lists of Contingency Results. And then it gives you options for grabbing. You can grab one set from a file where you've already run the contingency analysis and then saved it to an auxiliary file. And then you can grab the second set either from another file or from what's stored presently in memory. So your results that you just generated. And then if you click OK, then it gives you the option to change your display to add some comparison columns to the displays. And normally you'd want to do that. And then you can compare then the results, the before and after. Again, there's a more detailed example of that in another training course. So, information about that. Okay, and so next we'll kind of move into looking at building remedial action schemes. So everything we've looked at in contingency analysis thus far is stuff that always occur. Basically, every time you run the contingency analysis, all the actions, things that we've auto-inserted, for example, or even if you manually build a contingency and you don't add any criteria to it, every time you run that contingency, it will take all the actions that are part of the contingency. You can also have actions that occur only if the system meets a particular criteria. And there's two objects in Simulator that can be used to define these criteria. One is called model conditions. And model conditions are just simple filters that look at a particular element and compare that value in that element to a constant. Like, for example, maybe you want to see if the flow on an interface is greater than 200 megawatts. So you could create a model condition that does that. We'll see some examples of that in just a minute. A model filter is a way that you can make like Boolean logical combinations of different conditions. So maybe you want an action to occur only if the flow on an interface is greater than a certain amount and the output from a nearby generator is less than a certain amount. So you could create separate model conditions that check for each of those, and then you could have a model filter that has a Boolean AND of those two conditions in it. So then either one of those objects can then be used as a criteria which would evaluate then to either true or false. And then you can make remedial action scheme actions occur only if the criteria is true. So, okay, so this slide just describes then what model conditions and model filters are, and you can use those in contingency actions, remedial actions, or global actions, and the main use of them would be in remedial actions. That's kind of the feature that going forward is going to be supported in Simulator. So the action associating would be executed again only if the model criteria is met. And again, like a model condition is the comparison of a specific element to a quantity using an advanced filter. So for example, I mentioned, you could look at the flow of an interface and see if it exceeds a certain amount, or you can look at a bus voltage and see if it's equal to, less than, greater than, whatever kind of comparison you want with the filter, a certain value. These quantities can be compared to a constant, they can be compared to another parameter or another field, or they can be compared to the value of another object type called model expression. So we'll look at an example of that in just a moment. A model filter, again, is a logical comparison of one or more model conditions, or you can nest them as well. So you can have model conditions that make up model filters and then model filters that are used in other model filters. Here's an example that we can create for a model condition. Like, for example, let's say that there's certain actions that we want to take only if the flow on a particular transformer exceeds 190 MVA. So if we wanted to create that criteria, we could go in our contingency analysis to the options and then go underneath remedial action definitions and then choose model conditions. So right click on that, or I'm sorry, left click on that, come over here and right click in the dialog and choose insert. And if you want to create these, you don't have to worry about getting all of the parameters and the text exactly the same, because we'll do an example later in this section where we just load an auxiliary file that'll load all of these conditions in and give us an example of a remedial action scheme that way. But right here, if I want to create a new model condition, again, I get into this dialog and then I choose up here what element type I want. Because it's a transformer, I can choose the element type branch right here, and then I just pick the particular branch that I want from the list. So that would be the branch between bus 1152 and 1221, circuit ID 2. So I can just start typing 1152 and then look down the list. Right here is 1152 to 1221, circuit ID 2. It's a 230 kV to 115 kV transformer. So I pick the element up here, and then down here I basically create an advanced filter. In the case of where I want to compare the flow to a constant such as 190 MVA, I would choose as a field over here the MVA maximum. So I just start typing in MVA, choose MVA maximum, and then greater than 190. And you can add additional, just like building any other advanced filter, you can add additional conditions if you want. A lot of time with remedial action schemes, they're armed based on conditions in the reference state. So not necessarily in the, it can be based on conditions in the post-contingent state, but a lot of times, again, they're like armed based on what's measured on an ongoing basis under normal operating conditions. So within our contingency analysis, that would be in the reference state. So if you want to apply this filter and evaluate it in the reference state, then you check the box that says evaluate it in the contingency reference state. Otherwise, it would be evaluated in a post-contingent state if it were associated with a remedial action scheme. So in this case, I would want to check that. You can also do the opposite and disable whatever action is associated with this model condition if it's true in the reference state. And then you can even do this sort of thing like evaluate individual parts of this filter down here. So if you had additional actions, down here you can click add, or not additional actions, but additional conditions in your filter, then you can have some of them be evaluated in the reference state and some of them not if you wanted to. But we'll just do something simple where we're just comparing the flow on this transformer to a certain value and we're evaluating it in the reference state. So when I'm done creating it, I can click OK, and then I would give it a name, and I'll call it Hunterstown 230/115 kV greater than 190 MVA or something like that, something that tells me what it's doing, and then I click OK. And then it'll tell me, once I create it, it'll tell me whether or not that condition is presently met. And I can see if I go out, for example, using my bus view, one line, if I go to bus 1152, I can see that it's the flow on this line. And in our example here, this is a particular transformer that becomes overloaded for some outages on the 500 kV grid. The 500 kV grid is out here. Some outages over here cause additional flow to show up on the lower voltages at 230 and 115 kV. So this could be part of a remedial action scheme that's used to keep this transformer from being overloaded. This slide just then describes each of the options that we have on that dialog, and you can also check certain things like for topology. So I'm not going to go through and create, in this example, every single one of these conditions that are on a slide. What we will do to illustrate the example at the end is we'll load an auxiliary file that contains all these definitions, and then I can show you how it works. But this slide describes another condition that we could create to check and see if a particular 500 kV line is open. And in this case, what this would do is it would check if we decided to not evaluate it in the reference state, this condition would be true anytime any contingency resulted in the loss of this line. So it's not specific to any particular contingency, although it would certainly apply in the single outage of that line. It could be any contingency that I run that causes the outage of that line. So I can check to see if it's open, and if I want to check in the post-contingent state, then I wouldn't check this box that says to evaluate it in the reference state. I would leave that unchecked. And then the filter down here is I would check to see if the status is equal to open. So that's another thing you can do. And then you might also need to create a model condition that checks to see if the same line is actually closed in the reference state. So in other words, if you have a power flow case where that line is already out of service for maintenance and it's not a contingency that you're looking at, then you might assume that you've got a dispatch that already takes into account the fact that that line's not available. But if there's a contingency that forces that line out of service, then you might want to have a remedial action scheme that adjusts for that. So as part of that scheme, you might want to check to see if the line was closed in the reference state. So it's a similar condition, except it's evaluating in the reference state. So then, once you create several of these, again, you can look at them in this display and see whether or not they meet the conditions. And then you can also, like we mentioned, you can create a model filter. And we'll see this once we load all of these definitions by way of an auxiliary file. We'll see that there'll be some model filters in there as well. If you needed to create one manually, you simply go to the page under here called Model Filters, and you would right-click and insert one. And then for the model filters, you can basically just check one or more conditions or filters that you've already made, and you can add as many as you want. So I just have one added right now, but if I had other ones, I could include all of those, and then I can apply a Boolean logic from this listing up here to apply to these conditions. So you can have more complex criteria that would trigger a remedial action. So, and actually in our example, we'll have those where we're looking to see if a line is out of service in the post-contingent state, if it was in service in the pre-contingent state, and if the flow on a transformer exceeded a certain level. So that's the example depicted on this slide here, and we'll load that in. And then finally, if we want to, associate it with a remedial action scheme, we then build it into the remedial action as well. So we'll come back to that in just a moment. So in the filter that we discussed so far, we're just comparing the flow on a single transformer to a constant. You can also do more complex things if you want to. Like you can compare some quantity to the sum of the output of a generator plus the flow on a particular line. And there's not really one. You have to create an expression that represents that sum if you want to use it. And that's done under model expressions. And those are constructed similarly to custom expressions, which we looked at in the introductory training course. But they're here under model expressions. So you can click those, right-click, choose to insert. And you build these where you assign different quantities to variables. So if I wanted to go out and pick the flow on a transmission line or a transformer. I could assign that to a variable by clicking the define button, and then I can go out and find the field. So for example, I can find a particular transmission line and choose the field MVA, for example, and then assign that to variable x1. Maybe variable x2 is the value of a load somewhere. So I can pick that and then look at the load megawatts. And then maybe my expression is going to be like the sum of the two. So I would put in a mathematical x1 plus x2. And then it would calculate that. So you can do it as a mathematical expression. You can also do a lookup table. You can build the lookup table from the fields and then grab the value of the expression from the lookup as well. So if you need those, you can do those. We're not going to build on these really. In this example, our remedial action scheme is just going to look at directly measurable fields. So I'll hit cancel on that. So let's go ahead and load in the example, and then what we can do is we can look at some of these other features, like for the remedial actions as well. So, well, actually, before we do that, underneath the remedial action definitions, there's a list of remedial actions themselves, and you can create those and give them names just like you would for contingencies. So, and then generally you'd have these conditions in here. So I'm just going to go ahead and load one. If you needed to create one, you just right click in here and choose insert. And again, you build this just like you build a contingency. But again, it would be actions that would be applied anytime the associated criteria are met. So let's see what that looks like if we load the complete example. So down here in the lower left, I'll click the load button. And then I will go to under the directory S4 Advanced Contingency. I'll open that. And I first want to load a list of the contingencies. This is essentially the same list of contingencies we already inserted, but it's set up to not do any of the monitoring exceptions stuff, and it's also set up, I believe, to use the full power flow calculation method. If it's not, we can go back and change that. But I'll tell it that I want to load that first file, the CTG01 file, and then choose to delete the existing contingencies before adding the new ones. So it puts some new one. It puts the same contingencies in, and I think if I go to options, oh no, it didn't change it. Tell you what, let's just leave it right there. Let me look and see. Yeah, so if I go to the advanced limit monitoring, it's not going to re-report base case violations, and it's not going to do any of these other options right here. There's no monitoring exceptions, and I believe it also sets some limit monitoring settings. So if I go to my tools ribbon and I go to limit monitoring settings, I'll see what it did is it applied reporting to only areas 25 to 35 and at a minimum KV level of 100. So it's ignoring most of the elements except for the ones that are in those areas and at 100 kV and above. It's also using rating set B during contingency analysis. So if I go to my list of contingencies here and then click Start Run, and I sort this list in descending order by number of violations, I'll see there's 4 different contingencies that include at least one overload, and we're going to take a look at RAS that address 2 of these. The 2 are the Brighton to Constantine outage right here that has 2 violations, and the Constantine to Hunterstown. These are both 500 kV outages, and they're both ones that create overloads on lower kV elements. So for example, that Hunterstown transformer that we looked at with the model condition that we created, that's showing up as an overload here. And what we want to do is we want to see if the remedial action scheme does anything to correct that. So I will go to I'll go back to loading some additional definitions. So from the load button down here again in the lower left, I'll load this file that says S4 Advanced CTG02. And here, if it asks where it asks me if I want to delete the existing contingencies, I'll say no. And it'll simply add those other definitions. And some of the things that it added, if I go to the Options tab under Remedial Action Definitions, I'll see it added 2 remedial actions. And each remedial action includes multiple things. So one of them is called the Hunterstown 230/115 kV transformer. And this is a list of things with model criteria that it'll do. One of the things that it does is it drops generation by way of this injection group right here in this third action. It drops generation if this criteria is met. And this is actually a model filter. We'll see here, we manually created a model condition earlier. This loads that one plus a bunch of other similar ones. We can see there's one here that checks to see if the flow on the Hunterstown transformer is greater than 190 MVA. That's the one that we created earlier. And then there's also checks to see if it exceeds 220, so different thresholds. And then also ones that check to see if it's below certain values too. So all of these are used in the definitions inside the remedial actions. So, and then there's also a couple model filters which we looked in earlier. So for example, this model filter here has a few different actions in it. If I show its dialog, it refers to 3 different model conditions and ANDs them together. So it's going to check to see if this particular 500 kV line between Conditional and Hunterstown is open. It's going to check and see if the flow on the transformer exceeds 190 MVA, and it's also going to check to see if that particular element was closed in the base case. So this one's evaluating in the reference state. So is this one, and this one is not. So, and then it'll just AND all of those together. So, yeah, presently these aren't met, but if we run the contingency analysis, then some of those presumably might be met. On the much simpler conditions, which are just single checks, we can see that some of them are presently met and others are not met, but they would be met under certain contingencies. So what I could do now that I have these remedial action definitions in is I could see what actually happens if I run some of these contingencies now. In order to properly process these actions and properly look at the criteria, for a lot of them you have to be using the full power flow method, especially for things that are not checked in the reference state, for things that are checked in the post-contingent state, because it needs to actually calculate those quantities. If you use one of the linearized methods, and anything that it's really trying to calculate in the post-contingent state, it's just going to default to checking it in the reference state, which might not really be the way you want it to operate. And then just to improve the processing time, I might want to skip all of the contingencies except the ones that are creating these overloads right here. So I can go into my contingency records, and then under the skip column, I can, let's see, check that, and then toggle everything to yes, and then flip back to no, the skip field for these contingencies. Although the remedial action schemes are only going to address a couple of these. And then, well, I'll sort on the skip field now, so that when I run it again, it won't resort based on violations. Then I'll click the start run down here. And yeah, you can optionally just clear all the results for the ones that the skip is set to no. So I'll choose that. I only want to rerun those. So it's doing a full AC calculation method right now. It's going to take a little bit longer than it did when we did the other method. But I only have 4 contingencies, so it should run through pretty quickly. Okay, so it's done running right now. 2 of the contingencies that we had overloads in before, we didn't actually do any. We didn't have any remedial actions for, so those aren't shown. But these other 2, we notice now that we run it with remedial actions, there are no violations associated with them, so that's good. And then what we might want to do is check to see what actually occurred. So we can click, we have the combined table for what actually occurred, and then there's also a what actually occurred tab down here. So we could check that, and it tells us that in addition to, let me expand this a little bit here, in addition to the definition that's directly part of that contingency, it applied 3 other actions that are shown here as part of the remedial action schemes. So one of them was a gen drop. So it opened the generators that are in injection group Shawville because it met this particular model criteria here. And it tells me that it was part of a remedial action scheme. So, and then it tells me here that what ended up, 276 megawatts ended up getting dropped. And then there's also another one where some generation got increased. That's done for generation at a specific bus. So it was changed, its output was changed based on this model criteria right here. And then there was another load drop that was done. So that's one of the contingencies. And then the other contingency right here, this is the one where we started to make the model criteria for it manually before we loaded the auxiliary file. It looked at these different thresholds for the flow on the Hunterstown transformer. All those criteria were met, so it applied a gen drop and then also connecting and increasing the output from some other generators. So by making those changes, then we don't have any overloads. So that's the effect of running the remedial action scheme in this case. And then the slides just talk in some more detail some of the things that I kind of skipped over because we loaded the objects through the auxiliary file. It talks, okay, so this is kind of an important section right here. The element status, this was loaded in with the auxiliary file, but the model criteria inside these remedial action scheme actions has a status which is, it's shown here in the results. And then if I go back to the options and I look at the remedial actions right here, so there's a model criteria and an associated status. And that status, I can see, has values of check, always, never, post-check, topology check, or solution fail. And those different options are then explained on the slide. If you have a check status associated with the model criteria, then the action will be taken only if the model criteria is true, or if there's no model criteria associated with it. But if it's a remedial action scheme, you'll pretty much always have some sort of criteria because you don't want to always take those actions. You only want to take them if the criteria is met. If the status is set to always, then the associated action would be taken regardless of whether the model criteria is met. Never would be always skip it. Post-check, topology check, and solution fail are a little bit more involved. Post-check lets you make the condition conditional on a post-contingent system. So for example, if a particular branch is overloaded, then open it. So when these conditions exist, if you have some of these, like here's one right here, it's going to iterate through the other actions in the RAS, and it could apply it at any stage along the way. It'll check to see if any of the other actions were taken, and then it'll have to solve the power flow, and then see if any of the criteria for the post-check actions are met. So it's just explaining that it kind of loops. The topology check allows you to make an action conditional on a post-contingent state, but before the power flow is solved. I don't think we necessarily needed to do that for this particular set of examples, because I don't think it's a case where the power flow wouldn't solve, but it allows you, it's good to use on things anytime you're like taking a line out of service or dropping generation or things like that. So it's related to bus and branch statuses. So like these look to see if this is a model filter that it references that checks to see if the flow on a transformer exceeds a certain threshold and if a line was lost as part of a contingency. So that 500 kV line between Counterstone and Hunterstown. It's going to check to see if those conditions are met. With the topology check status, it'll check before it actually solves the power flow, but it'll check after the contingency is applied, which we want because we want to see if the line's out of service in the post-contingent state. So that's all part of the model filter. And again, recall that these model filters right here have multiple elements in them. And then some of these model conditions are evaluated in the reference state and others aren't. Like this one's evaluated in the reference state, this one's evaluated in the reference state, and this one isn't. So again, to know that for sure, we'd have to go back to the model conditions and we'd see here, some of these are evaluated in the reference state and others are not. And then you can also use this solution fail action, which would make the action conditional on whether or not the power flow actually solves. That's not used in this example here, but if it fails to solve the power flow at some stage, then it would take any solution fail action where the model criteria is met. Okay, and then also just getting even more involved, which again, we're not going to dive this deep into this example, but you can also do things with time delay, which really all this is useful for is telling it in what order to take the actions. So if you have some actions which have to occur before other actions are taken, you can put in various time delays, and those with a shorter time delay would be applied first, and those with the longer time delay would be applied last. With the contingency element definition or with the RAS element definition, if we go back here, if I pick one of these remedial action schemes and look at these elements, the default time delay is 0, which basically means there's no differentiation, but you can put in some values, and then you can also put in separate time delays for each one of these conditions that's inside of a filter. So again, and then this is just an example here where you have like different actions with different time delays. So it's just explaining that it's going to evaluate this before it evaluates this because there's a longer time delay in here. If you have time delays on actions and then time delays in filters, then there's a hierarchy as far as when it's used. And then there's also a yes/no field for whether or not an action is persistent. A persistent action would be like, once it's taken, then it'll apply the action anytime the model criteria is met. Okay, and then there's also some slides which explain there's some transient stability models that can be incorporated, particularly with switch shunts and line relays. Again, this is if you have the transient stability tool and you have these models present, they can be used to trip devices in the contingency analysis if the criteria is met that's associated with it. So if you want to evaluate the behavior of your line relays in contingency analysis, then you can do that too. And then this slide is just kind of a big summary for what order things are done. If you have like all these different types of statuses associated with criteria and different time delays and different transient actions, there's this big looping process that determines how those get solved. Remedial actions, of course, are containers that you can use for these conditional actions, which we looked at in the example that we loaded. And then these slides just explain more about how you can create a remedial action. It's the same as just creating any other contingency. Each individual remedial action is just a way of grouping these conditional actions, which are underneath them. So the WECC has a certain file format for the remedial actions. It's an auxiliary file format, but with specific object types and fields for the WEC format. So if you want, you can save. If you come down here and you click save, you can save everything to an auxiliary file. You can also save things to a WEC contingency and RAS definition, and as well as some of these other formats for PSSE and older Power World Simulator version formats as well, which are not commonly used anymore. Yeah, there's also a solve power flow action that you can insert. This is just put in here for reference. And then these next few slides detail the remedial action example that we just looked at by loading in those auxiliary files. So the first auxiliary file does these settings right here. It does apply some limit monitoring settings. It sets the B rating limit for contingency analysis and so on. And then there's remedial actions that get loaded to alleviate a couple of the outages that show up when you do the first contingency run. And then those are stored in this second auxiliary file that we loaded. And then you can explore those different definitions and so on. Gen drop and gen increase we recommend that you use injection groups to do that, because that way the definition is more robust depending on exactly which units are online. It just treats everything in the injection group as a big block that it can increase or decrease. So again, it makes the definition more applicable to different starting conditions that might exist in your case. So it's recommended to use injection groups for things like gen drop or increasing generation output. So, and then again, this is a look at the different elements within each remedial action. And then there's a filters associated with most of these in the model criteria column. And if you're doing this manually and you want to add a model criteria, you just double click on the model criteria, and then you can pick from any of the defined filters or conditions and assign those as criteria. Or you can click, there's a little button in the right with the ... on it. You click that, it goes through to, and if you want to clear that box, you can just click the remove, and that'll clear the criteria altogether. So again, the next few slides just explain in detail what's included in some of those remedial actions and some of those remedial action elements as well. And if we look in the message log too, it'll tell you things that got skipped for certain contingencies. So yeah, you can look in the message log as it's processing each contingency. It'll tell you which of the remedial actions were skipped or applied. So in the case of this contingency right here, it only applied the element from the contingency, and it skipped a lot of the other stuff. So, and if I scroll up, so this one got, yeah, this was one of the other two contingencies too. Those got skipped. If I scroll up to this one, it applied some actions right here, post-check actions. So yeah, if you really want to trace what happened, you can look in the message log here. I find it's usually good enough to look at the what actually occurred tab here, and you can see which remedial actions were applied. And then the final set of slides, which we're not going to go through here in detail, just explain how you can use some sensitivity analysis tools for identifying. This is mostly for operations engineers who might be tasked with developing a remedial action scheme. You can use sensitivity analysis, you can use our line loading replicator, or you can use the OPF with minimum control change. You first put the system in a post-contingent state and then look and see what possible actions might help relieve conditions that you want to relieve. The first set of slides looks at just simple TLR sensitivities along with some custom expressions that could be used. And then this example here on this slide looks at using the line loading replicator, where you pick an overloaded line and you try to bring it back to its limit, and then it'll tell you like which generators have the best sensitivity and merit order for dispatching. And then you can also look at OPF with minimum control change. So put it in the post-contingent state, run the OPF with minimum control change, and the OPF results will tell you which controls were changed and by how much, and you can kind of use that as a guide for which changes might be part of a remedial action scheme as well.
If you need further assistance, please feel free to look us up on the web, give us a call, send email to our support line, or if you prefer to work with a particular Power World engineer, please feel free to contact that person directly.